Look around you. Look at the world we have built. From the glowing canyons of our cities that scrape the sky, to the silent, intricate dance of satellites weaving a digital web around our globe. We have carved our story onto the face of this planet. Our agriculture has reshaped continents. Our industry has altered the chemistry of the atmosphere. Our presence is so profound, so pervasive, that geologists have coined a new epoch to describe our impact: the Anthropocene, the age of humans. We see our legacy as permanent, a story etched in steel and concrete, a signal so loud that it will surely echo through the ages. But what if this confidence is a form of temporal narcissism? What if the story we're writing is not the first grand narrative this world has hosted? What if we are merely the current tenants of a planet that has a long and forgotten history? Are they erasing its occupants? This is the fundamental, unnerving question we are here to explore, not as philosophers, but as engineers. We are here to ask, if an advanced industrial civilization existed on Earth millions of years before our own, what would it take to find them? Welcome to the ultimate cold case. We are not just looking for a needle in a haystack. We are looking for the ghost of a needle in a haystack that was vaporized, melted, and recycled millions of years ago. Our challenge is to engineer a method to prove they were here, to read the faint, whispered clues left behind on a planet that is an expert at erasing its past. The sheer mind-numbing scale of the problem is where we must begin. Our human timescale, the recorded history of a few thousand years, is an insignificant rounding error in the lifespan of the Earth. Our entire civilization, from the first clay tablets to the smartphone in your pocket, exists within a vanishingly thin sliver of geological time. To find a predecessor, we must look back not thousands, but tens, or even hundreds of millions of years. And in that gulf of time, the Earth becomes a relentless machine of destruction. The primary actor in this erasure is a process you learned about in school, but perhaps never considered in this terrifying context: plate tectonics. The Earth's crust is not a single solid shell. It is a fractured mosaic of immense plates, floating on a sea of molten mantle. This is not a gentle process. It's a planetary-scale conveyor belt. New crust is born in volcanic mid-ocean ridges, and old crust is consumed in subduction zones, where one plate is forced beneath another, diving back into the fiery interior to be melted and unmade. Now, why is this so important? The silent question, so what? The answer is devastating for our search. It means the very surface of the planet is temporary. Less than 2% of the Earth's current surface is older than the time of the dinosaurs. Any landmass, any continent where a civilization might have flourished 100 million years ago, has likely been dragged down into the mantle and completely obliterated. Imagine searching for the ruins of ancient Rome, only to be told that the entire Italian peninsula was melted into magma 60 million years ago. That is the scale of the challenge. The very ground they walked on is gone, but let's assume for a moment that some fragments of continents from that deep past did survive. Even then, they would face the wrath of a second tireless eraser: erosion. For millions of years, wind, rain, and ice have been sandblasting, grinding, and dissolving the surface of our world. Mountains that were once as majestic as the Himalayas have been worn down to gentle rolling hills. Canyons deeper than the Grand Canyon have been carved and then filled with sediment. This process is the arch nemesis of the archaeologist. It works from the top down, relentlessly scouring away the very layers where civilization would leave its mark. Think of it like a cosmic sander. A normal archaeological dig might sift through a few meters of soil to find a buried settlement. We would need to contend with the fact that kilometers of vertical rock have been stripped away from the landscape. Any city, any monument, any quarry, any physical structure would be the first thing to go, turned to dust and washed out to sea. This is why we don't find dinosaur cities. Their world, the very surface they inhabited, has been weathered away to nothing. And if erosion doesn't get you, the ice will. Periodic ice ages have sent colossal glaciers, kilometers thick, bulldozing across the continents. These rivers of ice are not gentle. They scrape the bedrock clean, pulverizing everything in their path and transporting the debris hundreds of kilometers away, scrambling the geological record into an almost indecipherable mess. The crime scene has not only been wiped clean, it has been churned, shredded, and redeposited in a completely different location. The evidence is not just gone. It's been scattered to the four winds. It is in the face of this near-perfect erasure that a profound and daring idea was born, known as the Silurian Hypothesis. Formulated by astrophysicist Adam Frank and NASA climate scientist Gavin Schmidt, it is one of the most brilliant thought experiments of our time. It is named after the Silurians, a fictional race of intelligent reptiles from the classic Doctor Who television series who existed on Earth millions of years before humanity. But this is not science fiction. This is a rigorous scientific question. The hypothesis does not claim that such a civilization existed. Instead, it asks something far more practical, something an engineer can truly sink their teeth into. If an industrial civilization existed in the deep past, what kind of traces could it possibly leave behind? How would we design an experiment? To find it, the core of the hypothesis is a paradigm shift. It tells us to stop looking for the obvious. Stop dreaming of finding the fossilized ruins of a skyscraper or the metallic shell of an ancient vehicle. The odds of such a macrofossil surviving the meat grinder of geology for 60 million years are so infinitesimally small as to be effectively zero. We must look for something far more subtle, yet potentially far more widespread. We must look for the fingerprints of industry itself. We must look for a technosignature. What is a technosignature? This is the key that unlocks the entire puzzle. A technosignature is not the technology itself, but the indirect planetary scale consequence of that technology. It's the difference between finding a fossilized car and finding a strange layer of rubber compounds and blood additives in sediment cores worldwide. The car is gone, but the pollution it created is now part of the geological record. This is the EDI moment of the entire concept. Why is this important? Because while a city is a localized phenomenon, easily erased, the waste products of an industrial civilization can be global. They get into the air, into the water, into the food chain, and eventually they settle into sediments at the bottom of oceans and lakes all over the world. These sedimentary layers are the planet's hard drive. Layer by layer, they record the history of the Earth's chemistry. While plate tectonics might destroy much of this record, some deep ocean basins can remain relatively undisturbed for hundreds of millions of years, preserving this chemical history. So our engineering challenge transforms. We are no longer geological archaeologists looking for a lost city. We become planetary chemists, drilling deep into the Earth's crust to read a chemical barcode, looking for a single anomalous line that says, "We were here." We are looking for the chemical ghost of their world, not the physical one. This is where the true engineering blueprint begins to take shape. We are not on a treasure hunt. We are on a forensic investigation. We must design a program to look for specific unnatural anomalies in the geological strata. What would these anomalies be? We can use our own civilization, the Anthropocene, as a template. What signatures are we leaving behind right now that might be detectable in 60 million years? The list is our guide. We would look for sudden spikes in carbon isotopes, indicating a massive unnatural release of fossil fuels into the atmosphere. We would search for exotic, stable synthetic molecules that have no natural origin, the paleoplastics. We could look for unusual concentrations of nitrogen, a sign of continent-scale fertilizer use from an advanced agricultural society. We could even look for the rarest of traces, long-lived radioactive isotopes, like plutonium-244, which could be the unmistakable signature of a nuclear industry, or even a nuclear war that ended eons ago. The presence of any one of these might be a fluke, an unexplained natural phenomenon. But finding a cluster of these anomalies, all occurring in the same thin geological layer around the world, that would be the engineering proof. It would be a signal in the noise. It would be the echo of a forgotten industrial age. This is the path forward. It is a plan to scan not just a single site, but the entire planet's history, written in the language of rock and chemistry. So, this is our mission. We stand on the shoulders of a planet that has mastered the art of forgetting. Our task is to teach it to remember. In this deep dive, we will move from this theoretical framework to a concrete engineering plan. First, we will examine the specific materials and chemical signatures we must hunt for, the foundation of our search. Then, we will outline the colossal logistical and technological plan of construction. How do we actually drill, sample, and analyze on a global scale? We will then confront the immense operational challenges and potential points of failure, the things that could lead us astray or fool us into seeing a ghost where there is none. And finally, we will dare to contemplate the civilizational impact, the breathtaking consequences for humanity if we were to succeed, and prove once and for all that we are not the first. The journey into Earth's deep past begins now. Every engineering project begins not with steel and rivets, but with a blueprint, a plan. For our unprecedented challenge, the blueprint isn't drawn on paper, but in the language of chemistry, geology, and physics. Before we can design the drills and the sensors, we must first define the signal. What precisely is the unnatural signature we are hunting for in the geological record? This phase is our theoretical foundation. It's where we move from the grand, abstract idea of a lost world to a concrete, itemized list of evidence. We are building the forensic kit we will use to dust for the fingerprints of a ghost. Our investigation will focus on 4 primary categories of evidence, each a potential echo of a long-gone technological society. Our first and most fundamental target is written in the single most important element for life as we know it, carbon. We are looking for a disruption in the planet's carbon BARCODE. Life on Earth has a distinct chemical preference. Of the main carbon isotopes, carbon-12 and carbon-13, living organisms, particularly plants, find it slightly easier to absorb the lighter carbon-12. Think of it as a subtle dietary choice on a planetary scale. For hundreds of millions of years, the biosphere has been preferentially packing away C12 into organic matter. So, when this organic matter ancient forests, plankton blooms gets buried, compressed, and cooked into fossil fuels like coal, oil, and natural gas. It creates vast underground reservoirs that are artificially rich in this lighter C12. This is the crucial setup for our first piece of evidence. Now, what happens when an industrial civilization discovers these reservoirs and begins burning them for energy on a massive scale? The answer is a chemical thunderclap. They would release colossal quantities of this C12-rich carbon back into the atmosphere in a geological instant. So what? Why does this matter? Because that sudden flood of C12 would temporarily change a carbon signature of the entire planet. The atmosphere, the oceans, and every living thing that breathes that air or lives in that water would suddenly see its ratio of carbon-13 to carbon-12 plummet. This sharp negative dip is called a C excursion, and it gets recorded in the sediments that form year after year on the ocean floor. It is, in effect, a chemical scar. The analogy is a global accounting ledger. For eons, the carbon budget is balanced. Then, in one entry, corresponding to a single thin layer of rock, the books are wildly out of balance. We see a massive withdrawal from the planet's fossil carbon savings account, a withdrawal so fast that it can only be explained by a deliberate technological process. We are living through such an event right now. It's called the Swiss effect. By looking for this exact signature in the deep past, we are holding up a mirror to ourselves, searching for the reflection of another civilization that made the same. Energy choice we did. Our second category of evidence moves from the elemental to the synthetic. We are searching for unnatural molecules, the chemical equivalent of finding a microchip in a dinosaur bone. Nature is a master chemist, capable of producing an incredible diversity of molecules. But it follows certain rules, favoring efficiency and biodegradability. An industrial civilization, on the other hand, creates for novelty and durability. This leads to the production of compounds that nature simply does not make. This is where we hunt for the ghosts of paleoplastics and their chemical cousins. While a plastic bottle is unlikely to survive for 60 million years, its constituent molecules, or their stable breakdown products, might. We'd be looking for unusual concentrations of long-chain, hydrocarbon polymers or complex aromatic compounds in sedimentary layers that have no plausible natural origin. But even more compelling would be the discovery of artificial molecules, designed for extreme stability, like chlorofluorocarbons, CFCs, or other halogenated organic compounds. These molecules are so alien to natural biochemistry, and so resistant to degradation, that they are a near-perfect technosignature. They have no known non-technological source in the universe. Finding a pocket of ancient air trapped in rock salt, or a preserved sediment core containing even trace amounts of freon, would be as unambiguous as finding a signed photograph. The so what here is monumental. A carbon anomaly could, in theory, be caused by a massive natural methane burp from the ocean floor. But a CFC molecule? That is not geology or biology. That is chemistry. It is proof of a laboratory. It's the molecular artifact that proves intelligent, deliberate synthesis. It's the indelible ink of a technological civilization, a message that says not only we lived, but we built. It is a sobering thought that the very pollutants we created and then struggled to ban from our own atmosphere because of their destructive power might be the most enduring and clearest message we are sending into the deep future. The third pillar of our theoretical foundation is the most potent and perhaps the most terrifying. We must search for the nuclear ghost. The process of harnessing atomic energy, whether for power or for war, creates a unique and indelible radioactive fallout. The universe, through supernovas, creates a background tapestry of heavy elements. But nuclear technology weaves its own unique threads into this tapestry, producing isotopes that are otherwise vanishingly rare or non-existent in nature. Our prime candidate is plutonium-244. This specific isotope is produced in significant quantities by nuclear reactors, but it has an astonishingly long half-life, 80.8 million years. This is the perfect temporal sweet spot. It's long enough to survive from the time of the dinosaurs, yet short enough that virtually all of the Earth's primordial, Pu-244 from its formation, has already decayed away. The natural background level of Pu-244 is therefore almost zero. Think of the Earth's geological record as a long, silent audio recording. Natural radioactivity is the constant, low-level background hiss. A global nuclear event, be it a series of atmospheric tests, a catastrophic meltdown like Chernobyl, or an unimaginable nuclear war, would be a sudden, sharp ping in that recording. The so what is that finding a globally distributed, thin layer of sediment enriched with Pu-244, or other long-lived transuranic isotopes like curium-247, would be the holy grail of our search. It's a signature that is not only technological, but marks a very specific and high level of scientific achievement. It tells us that this precursor civilization didn't just have steam engines, they unlocked the atom. This carries a heavy human weight. The discovery of this signature would be a message from a civilization that stood on the same precipice we do now, grappling with a power that could either fuel their future or end it entirely. Finding their nuclear ghost would force us to ask a terrifying question. If they were here, where did they go? Finally, our fourth category of evidence broadens the search from the chemical to the geological. A truly global industrial civilization doesn't just produce waste, it actively reshapes the planet. We're looking for the scars of this planetary engineering. One of the most profound signatures of our own Anthropocene is the disruption of the global nitrogen cycle. The invention of the Haber-Bosch process in the early 20th century allowed humanity to pull nitrogen out of the air and turn it into fertilizer on an industrial scale. This fueled a population explosion and a global agricultural revolution. It also flooded the world's ecosystems with reactive nitrogen, a signal that is now being recorded in sediments worldwide. A spike in nitrogen isotopes in a geological layer, coinciding with our other markers, would be evidence of a sophisticated, planet-spanning agricultural system. Another geological scar would be the footprint of their resource extraction. A technological civilization is a hungry one. It needs metals, rare earth elements, and building materials. This requires mining, quarrying, and construction on a vast scale, which in turn leads to a massive increase in erosion. We would look for evidence of this in the form of what geologists call anomalous sediment pulses. Imagine a sudden, thick layer of silt appearing in deep ocean cores around the world, a layer enriched with unusual concentrations of metals like copper, lead, and zinc, or rare elements essential for electronics. The analogy is simple. It's like a massive construction project next to a pristine lake. For years, the water is clear. Then, for a short period, the water becomes muddy and filled with strange debris. That layer of mud at the bottom of the lake is the permanent record of the construction. This is a crucial piece of the puzzle because it tells us about behavior and scale. It demonstrates a civilization's ability to alter planetary scale geological processes to meet its needs, a sign that they too had become a geological force in their own right. Finding these scars would be like finding a kindred spirit in ambition, a silent acknowledgement across the eons from one world-shaping species to another. These four pillars, the carbon barcode, the synthetic molecules, the nuclear ghost, and the geological scars form the theoretical bedrock of our search. Is our materials list. This is our blueprint. Now, we can begin to design the machine that will conduct the search. An idea, no matter how profound, remains a ghost until it is given form and substance. We have our theoretical blueprint, our list of chemical and geological ghosts to hunt. Now, we must build the machine to conduct the hunt. This is the logistical heart of our entire endeavor, a phase where we engineer the physical process of discovery. This is not a simple task of digging a hole. It is a multi-stage, globe-spanning project that must be designed with the precision of a space mission. Our construction and logistics plan can be broken down into three critical, sequential operations. First, pinpointing our targets with surgical precision. Second, deploying the technology to reach and recover the evidence. And third, creating a system to process and analyze the retrieved history of an entire planet. This is the engineering of the search itself. Our first step is project scoping and site selection. The Earth is a colossal library, but most of its books are damaged, unreadable, or lost. We cannot afford to drill randomly. We must find the pristine, untouched volumes. The question is, where are the geological sanctuaries? Where on this planet has the geological record been preserved with the highest fidelity for over 60 million years? To answer this, we launch a massive computational geology initiative. Using a combination of modern seismic imaging, which acts like a planetary-scale ultrasound, and advanced paleogeographic modeling, we begin by mapping the Earth as it was. We rewind the clock on plate tectonics, watching continents drift apart, and oceans open and close in our supercomputers. The goal is to identify regions of the ocean floor that have remained remarkably stable, deep, and undisturbed for eons. The ideal locations are what geologists call anoxic basins. These are deep depressions in the seafloor where the water is stagnant and contains very little oxygen. Why is this critical? The answer is preservation. In oxygen-rich environments, the seafloor is teeming with burrowing creatures that churn and disturb the sediments as they fall, blurring the historical record. But in an anoxic environment, there is little to no life. Each layer of sediment falls gently on top of the last, one after another, like pages laid carefully in a book. The analogy is stark. Trying to read history from a normal ocean floor is like trying to read a book that's been used as a doormat in a train station. The pages are torn, smeared, and out of order. An anoxic basin is a book that was sealed in a vacuum-tight vault the day it was printed. It offers a timeline of unparalleled resolution. The so what? Here is that this initial phase of digital exploration, of mapping and modeling, is the single most important part of the entire construction. Plan. The quality of our targets will determine the success of the entire mission. It is an immense data analysis challenge that will require us to build one of the most comprehensive models of Earth's history ever attempted. Once our prime targets have been identified, perhaps a dozen deep, silent basins scattered across the globe, we move to step 2, the global drilling and recovery program. This is where digital plans become physical reality. We need to assemble a dedicated fleet of scientific drilling vessels, the technological successors to ships like the famed Joy D's Resolution. These are not simple oil rigs designed for brute force extraction. They are floating, stable platforms of advanced science, capable of maintaining their precise position in the open ocean for months on end using sophisticated dynamic positioning thrusters that counteract every wave and current. They are, in essence, stationary scientific outposts in the middle of nowhere. The centerpiece of these vessels is the drill itself. Our engineering requirement is to extract a continuous, undisturbed core of sediment and rock from as deep as 3 kilometers beneath the seafloor, which itself might be 5 kilometers below the ship. The technology for this is breathtaking. We use a combination of rotary and piston coring systems. Imagine a device that drills a hole with an outer pipe while simultaneously pushing a thinner inner pipe into the fresh sediment ahead of the drill bit. This inner pipe captures a perfect, clean cylinder of geological history. It's less like a drill and more like a colossal, high-tech biopsy needle, carefully removing a sample of the planet's memory without damaging it. The logistics of this operation are staggering. It's a global ballet of supply ships ferrying fuel, food, and equipment, helicopter flights for crew rotations, and a robust, high-bandwidth satellite link to a central mission control. This command center would operate 24/7, coordinating the fleet's movements, monitoring drilling progress in real time, and managing the initial flood of data from the core samples. The sheer scale is comparable to the largest international scientific collaborations in history. This phase is the muscle. It's the physical manifestation of our will to know. A fleet of specialized machines built for one purpose: to reach back into the abyss and bring a piece of deep time to the surface. This brings us to our third and final step in the construction plan, a process I call the assembly line of discovery. We have successfully recovered thousands of meters of gray, muddy rock from the bottom of the ocean. The treasure is in our hands, but it is still locked away. How do we process this raw material to find a signal that might be composed of just a few hundred anomalous atoms out of trillions? The answer is to engineer a systematic, semi-automated analysis pipeline. No team of humans could manually inspect this volume of material with the required precision. We begin by establishing several globally distributed core repositories. These are state-of-the-art, climate-controlled libraries, not for books, but for the physical history of Earth. Here, the cores are carefully sliced in half lengthwise. One half is the working half for analysis. The other is the archive half, preserved for future generations to study with technologies we haven't even invented yet. The working half then enters the high-throughput scanning stage. Think of it as a CT scan for the Earth's core. Automated machines slide the core through a gauntlet of non-destructive sensors. X-ray fluorescent scanners map its elemental composition millimeter by millimeter, looking for unusual metal concentrations. Magnetic susceptibility sensors detect changes in mineralogy that could indicate strange events. High-resolution cameras create a perfect digital image. This initial scan is our triage. Its purpose is to flag any layer, no matter how thin, that deviates from the boring natural background. The so what is that this automates the search for the needle in the haystack. The system tirelessly scans for any anomaly that deserves a closer look. When the scanners get a hit A, sudden spike in a strange metal, a weird isotopic ratio in the initial scan, a paper-thin layer of black material that doesn't belong, we move to the final and most exciting part of the assembly line, the biopsy. A robotic arm extracts a tiny gram-sized sample from the anomalous layer. This tiny piece of dust is where the discovery will be made. It is sent to the most powerful tool in our arsenal, the mass spectrometer. A mass spectrometer is, simply put, a molecular scale of almost supernatural sensitivity. It uses powerful magnetic fields to sort individual atoms and molecules by their mass. It is here that we will definitively answer our questions. Is the carbon in this layer skewed towards the lighter C12, the sign of fossil fuel burning? Does this dust contain even a few hundred atoms of plutonium-244, the ghost of a nuclear reactor? Does it harbor complex synthetic molecules that have no place in the natural world? The mass spectrometer will tell us. It provides the unambiguous quantitative data that can turn a wild hypothesis into a proven fact. This entire process, from the global mapping to the final atomic count, is our machine. It's a distributed, planet-spanning instrument designed for a single purpose: to read the autobiography of Earth and find the chapter that we thought was missing. This is the plan. It is ambitious, it is costly, but it is not impossible. It is an engineering challenge, and engineers live to solve the impossible. In the grand theater of cosmic engineering, optimism is our fuel, but rigorous pessimism is our navigation system. We have designed our theoretical blueprint and our logistical machine. Now we must stress test it. We must ask the most difficult question in any ambitious project. How could this all go catastrophically wrong? This is not an exercise in doubt. It is an exercise in building confidence. True confidence in an engineering plan comes not from ignoring the risks, but from staring them directly in the face and designing systems to mitigate them. In this phase, we confront the three great dragons that guard the treasure of deep time: the siren call of the false positive, the silent corruption of contamination, and the all-too-human challenge of keeping such a monumental effort alive. This is our operational hazard analysis. Our first, and perhaps most intellectually terrifying challenge, is the problem of the geological mimic. What if we find exactly what we're looking for, but it was created by nature, not by intelligence? This is the ultimate point of failure, the risk of misinterpreting a natural anomaly as a technosignature. Nature, after all, is a far more clever and versatile chemist than we often give it credit for. Consider our primary piece of evidence, the sharp negative carbon isotope spike. We believe this is a key sign of industrial-scale fossil fuel burning. But could a rare, catastrophic geological event create a similar signature? Imagine a massive undersea deposit of methane clathrate's frozen methane gas, destabilized by a nearby asteroid impact, releasing a colossal burp of C12-rich methane into the atmosphere in a geological instant. The resulting chemical scar in the rock record could look remarkably similar to an industrial revolution. Or consider our search for nuclear isotopes. In Oklo, Gabon, we have proof that nature itself, 2 billion years ago, created a series of spontaneous, self-sustaining nuclear fission reactors when groundwater flooded a uranium deposit with just the right geometry. While these natural reactors didn't produce the plutonium-244 we're looking for, they are a humbling reminder that nuclear physics is a part of the universe, not just a human invention. Could a unique combination of elements and circumstances in the deep past have created some of our other target isotopes? It is a possibility we must consider. The engineering solution to this profound challenge is not to trust any single piece of evidence. Our mitigation strategy is built on a single powerful principle, the consilience of evidence. The word consilience means the jumping together of knowledge, the unification of evidence from different, independent sources to form a strong conclusion. It is the core of modern scientific proof. Finding an anomalous carbon spike is interesting. It's a clue. But finding a carbon spike in a thin geological layer, which also contains traces of synthetic, halogenated paleoplastics, which also contains a globally distributed layer of plutonium-244, which also corresponds to a massive spike in heavy metal deposits from erosion, and which also shows a disruption in the nitrogen cycle that is no longer a clue. That is a conclusion. The analogy is simple forensics. A single fingerprint at a crime scene could be a coincidence. But finding the suspect's fingerprint, DNA, shoe prints, and personal belongings all at the same scene builds an undeniable case. We are not looking for a single geological fingerprint. We are looking for the entire forensic profile of a civilization. The so what here is that this establishes an incredibly high but necessary bar for discovery. It's our shield against wishful thinking. Any potential discovery would face the most intense scientific scrutiny imaginable, and a single line of evidence would never be enough to survive it. Our entire operational plan must be built around finding not one signal, but a chorus of signals, all singing the same unambiguous song. Our second great dragon is a more insidious, practical threat, the problem of contamination and degradation. We are searching for chemical signals at the parts per billion or even parts per trillion level. At this scale, the modern world is screaming with the very contaminants we are trying to find. The risk of our own civilization's chemical signature bleeding into our ancient samples is immense. This challenge exists at every stage of the operation. At the drill site, the very metal of the drill bit, the lubricants used in the machinery, the hydraulic fluids, even the diesel exhaust from the ship itself can introduce a shower of modern hydrocarbons and metallic particles onto our pristine core. The sample could be contaminated before it even leaves the seafloor. Then, once on board, a single microscopic fiber from a scientist's fleece jacket or a flake of paint from the laboratory wall could corrupt a sample being analyzed for paleoplastics. This is not a trivial concern. It is the nightmare scenario that keeps geochemists awake at night. Furthermore, even if we retrieve a perfect sample, we must contend with the degradation of the signal over time. The geological process of diagenesis, the slow cooking and squeezing of sediments. into rock can cause molecules to break down and isotopes to migrate between layers, blurring a once sharp signal into a faint, ambiguous smudge. Our clear, definitive ping could be smeared by time into a useless hum. To combat this, our engineering plan must incorporate a level of purity and containment that borders on the fanatical. This is an engineering challenge of extreme cleanliness. Our drilling systems must be completely redesigned for scientific purity. This means using diamond-tipped drills that shed almost no material, and developing closed-loop systems that use ultra-filtered, chemically inert drilling fluids with real-time chemical sensors that would instantly sound an alarm if a modern contaminant was detected. The analogy is the difference between a construction site and a surgical suite. You cannot perform a delicate transplant in a dusty workshop. Similarly, we cannot conduct this delicate search with standard industrial equipment. Every part of the process must be hermetically sealed. Our core handling labs, both on the ships and ashore, must be built to Class 100 cleanroom standards, the same used to fabricate computer microchips. All air is filtered, all surfaces are sterile, and the most sensitive analyses would be performed by robots inside nitrogen-purged glove boxes to eliminate any possible contact with the modern world. The importance of this cannot be overstated. Any positive result we find will be meaningless unless we can prove, beyond any shadow of a doubt, that it was not a result of contamination. Our data's integrity is the bedrock of the entire project's credibility. Without these extreme measures, any potential discovery would be dismissed, and rightly so. Finally, we face our third and most unpredictable dragon, the human factor. This is the challenge of economics, politics, and focus. A project of this magnitude would be one of the most expensive scientific undertakings in human history, costing billions of dollars and taking decades to complete. It requires stable, long-term funding and peaceful international cooperation on a scale that is often difficult to maintain. What happens if a global recession forces budget cuts? What if geopolitical tensions cause key partner nations to withdraw? What if the public, or the politicians who represent them, simply lose interest in a project whose primary payoff may be a generation away? This is, in many ways, a more complex engineering problem than drilling 3 kilometers into the Earth's crust. It's a problem of social and political engineering. The mitigation strategy must be built into the project's very structure. It cannot be the project of a single nation. It must be a truly global human endeavor, like the International Space Station or CERN. By distributing the cost and the ownership, we make the project more resilient to the shifting priorities of any single government. Furthermore, the project must be designed to deliver a continuous stream of valuable intermediate discoveries. The high-resolution climate data from these cores would revolutionize our understanding of past climate change. The advances in drilling, robotics, and sensor technology would have countless spin-off applications. We must demonstrate a constant return on investment to our stakeholders, proving the project's value long before we answer the ultimate question. This is the great operational challenge. It reminds us that our greatest explorations are enabled, not just by our technology, but by our ability to cooperate and maintain focus on a distant goal. It is a challenge worthy of the question we are asking. For every great engineering project, there is a purpose, a why, that drives the immense effort of the how. We have meticulously designed the machine to search for a ghost in the rock. We have stress-tested our plan against the dragons of doubt and failure. Now, we must dare to imagine success. What happens on the day after discovery? What is the impact on the human psyche, on our civilization, on the future of our species? When we receive a definitive, verified message from across an ocean of 60 million years that says, "You are not the first," this is not merely a scientific discovery. It is a species-level event. It is a fundamental rewriting of the human story, and its impact would be the single greatest paradigm shift in the history of our consciousness. The world before that discovery and the world after would be two completely different planets. Imagine the moment. A press conference is called, but it is not held by a single agency or university. It is a global broadcast, a unified statement from the world's leading scientific bodies. The data, vetted for years, is presented in a geological layer precisely dated to the end of the Cretaceous period. Found in a dozen core samples from around the globe, the consilience of evidence is undeniable. The carbon spike, the synthetic polymers, the nuclear isotopes. The message is clear. An advanced industrial civilization existed on Earth before the asteroid that wiped out the dinosaurs. In that single moment, human loneliness ends and human humility begins. For our entire existence, we have operated under the assumption that we are a cosmic singularity. We are the planet's first and only experiment in high technology. The discovery would shatter this illusion forever. The Fermi paradox, the question of where is everybody, would be answered in the most haunting way imaginable. They were right here. We are no longer the lonely child of an empty planet. The analogy is profound. It is like an orphan growing up, believing they are utterly alone, only to discover at age 30 the faded photograph of an older sibling who lived and died long before they were born. The sense of self, the entire narrative of one's own existence, is irrevocably changed. The house you thought was yours is suddenly filled with the echoes of another's life. This would trigger a renaissance in philosophy, art, and religion, a desperate global scramble to understand our new context. Our history is not the history. It is round two. Our Anthropocene is not a unique event. It is a recurring planetary cycle. This is a humbling on a scale we cannot fathom, a necessary check on a species that has long believed it was the pinnacle of creation. The second, and more terrifying, impact would be the reframing of our future. The discovery of a failed predecessor is a chilling piece of evidence in the great cosmic debate about the Great Filter. The Great Filter is the hypothesis that some step in the evolution from simple life to a galaxy-spanning civilization is so difficult that almost no species ever makes it past. For decades, we have hoped that the filter was behind us, that the emergence of complex life, or intelligence, was the hard part. The existence of a Silurian civilization proves that wrong. They made it. They built an industrial world. They became a geological force, and they are gone. This is a stark, terrifying warning. It means the Great Filter is likely still ahead of us. Their tombstone is a signpost on the road ahead, and it points to a cliff. The geological layer containing their technosignature would instantly become the most precious and intensely studied artifact in human history. It ceases to be a geological curiosity and becomes a black box recorder from a failed civilization. Our entire scientific apparatus would pivot to forensic planetology. The exact nature of their demise, encoded in their chemical legacy, would become the single most important dataset for ensuring our own survival. If their end was marked by a catastrophic carbon spike, ocean anoxia, and a biodiversity collapse, it provides a terrifyingly clear echo of our own climate crisis. Their fate would provide a data-driven argument for global cooperation on a scale we have never achieved, because the consequences of failure would no longer be a computer model. They would be written in the rock beneath our feet. Or consider the darker scenario. If the primary signature we found was the nuclear ghost, the plutonium-244, and other isotopes, the implication would be even more profound. It would suggest that they fell into the trap of their own weaponry, that their final act was one of global self-destruction. This discovery would echo through the halls of every government and military command on Earth. It would reframe the debate on nuclear disarmament from one of idealism to one of demonstrated existential necessity. Their atomic ashes would serve as the ultimate cautionary tale, a message from a civilization that faced the same demons we do and lost. The so. What? Here is monumental. For the first time in our history, our conversations about existential risk would not be theoretical. We would have a data point, a single, tragic, invaluable data point on civilizational longevity. This knowledge would change everything. It would be a unifying force born from terror, a sudden collective realization that our petty conflicts and national rivalries are utterly insignificant in the face of the demonstrated filter that lies ahead. Their failure could be the very thing that saves us from repeating it. The third wave of impact would be a revolution in the life sciences. The question would shift from how did they die to did anything of them survive? This would ignite a new kind of biology, a search for a ghost biosphere. Geneticists would begin an unprecedented project to sequence and cross-reference the genomes of life on Earth, especially extremophiles, organisms living in the deep crust, in volcanic vents, in environments we once thought sterile. We would be searching for biological anomalies, for genes or entire organisms that seem disconnected from the known tree of life. Could it be that they engineered life? That some of the hardiest organisms on our planet are not our cousins, but the descendants of their biological experiments, or even their pets? The analogy is finding a single sentence written in perfect Latin within an ancient Egyptian hieroglyphic text. It would prove a cultural and biological exchange we never dreamed was possible. This would also transform our approach to artificial intelligence. The discovery of a non-human intelligence on Earth proves that consciousness is not a fluke of primate evolution. It could be a convergent property of complex systems. It forces us to ask, were they biological? Or did they, perhaps, create their own successors? Does intelligence, once it reaches a certain threshold, inevitably move from a biological substrate to a synthetic one? The AIs we are building would no longer be seen as mere tools, but as potential participants in this recurring planetary cycle of intelligence. We would have to confront the possibility that we are not creating the next human technology, but perhaps the next Silurians. Finally, the long-term civilizational impact would be a reorientation of our destiny. The discovery would give humanity a new unifying cathedral project, a multi-generational quest to learn everything we can about our predecessors. This quest would drive our exploration of the solar system with a renewed, almost holy purpose. We would no longer be looking just for rocks and ice on Mars or Europa. We would be looking for them. Did they leave a message? An artifact? Could they have established an outpost on the moon, a place free from the recycling engine of plate tectonics? The moon would suddenly become the most important archaeological site in human history. Our drive to become a multi-planetary species would be imbued with a new urgency. It would no longer be a grand, optimistic vision, but a necessary survival strategy, a lesson learned from the civilization that put all its eggs in one planetary basket. The ultimate impact of finding we are not the first is that it would give us a new creation myth, one written not by prophets, but by the planet itself. It's a story that says intelligence is a property of this world, a fire that has been lit more than once. Our ultimate purpose, our greatest engineering challenge, would be clear: to become the first children of Earth, to not only understand that fire, but to carry its flame safely to the stars. We began this journey with a question that felt like it belonged more to science fiction than to a serious engineering analysis. What if we are not the first? We stood at the edge of the immense, silent ocean of geological time and wondered if other ships had sailed these waters before us. From that single fantastical question, we have engineered a tangible path forward. We have charted a course from a dream to a potential reality, transforming a ghost story into a blueprint for discovery. Our journey has taken us through the very heart of what it means to be a thinking, building species. We moved from the abstract to the concrete, from the what if to the how to. We first established our theoretical foundation, learning the specific language of a potential predecessor. We designed the lexicon of our search, defining the carbon scars, the synthetic molecules, the nuclear ghosts, and the planetary scars that would constitute a message from the deep past. We learned what to look for. Then we moved into the realm of logistics and construction, designing the globe-spanning machine of drilling vessels, pristine laboratories, and automated analysis pipelines capable of executing this search. We built the physical plan, detailing how to look. With our plan in hand, we subjected it to the crucible of criticism, confronting the immense operational challenges of geological mimics, pervasive contamination, and the sheer human difficulty of such a long-term project. We learned how to be sure of what we find. And finally, we dared to contemplate the civilizational impact, the species-altering metamorphosis we would undergo upon discovering that our history is not our own. We understood why we must look. Through this entire process, a deeper meaning of our engineering endeavor has emerged. This project, in its purest form, is not an act of construction. It is an act of listening. We live in an age defined by our own noise, the roar of our engines, the chatter of our digital networks, the ever-expanding footprint of our presence. We have become masters of shouting our existence into the cosmos. But this project calls for a different kind of mastery. It calls for the engineering of silence and sensitivity. It requires us to use our most advanced technology, not to transmit, but to receive. To build instruments of such profound sensitivity that they can detect the whisper of a forgotten world beneath the noise of our own. We began by framing the Earth as an antagonist, a planet that erases its past. But perhaps we were wrong. Perhaps the Earth forgets nothing. Perhaps it is simply a library where the books are written in a language we have not yet learned to read. Our entire grand globe-spanning engineering project is, in the end, a Rosetta Stone, a machine designed to translate the silent, patient language of geochemistry and rock strata into the human language of history, meaning, and warning. The analogy is that of an astronomer. For centuries, we could only look at the stars with our own eyes. Then we built telescopes, instruments that allowed us to gather the faint, ancient light from distant galaxies and read the story of the universe. This project is a telescope pointed not at the sky, but at the ground beneath our feet, designed to gather the faint, ancient signals of deep time and read the story of our own world. In the end, this grand search can only have one of two outcomes, and the intellectual and philosophical honesty of our engineering approach demands that we confront both. The first possibility is that we succeed. We find it, the unambiguous, verified, multi-pronged evidence of a precursor civilization. As we've explored, this discovery would change everything. It would end our cosmic loneliness, gift us a terrifying but vital lesson about the Great Filter, and provide a new, unifying purpose for our species. It would be the single greatest discovery in the history of science, a moment that would cleave human history into a before and an after. But the second outcome is just as profound. What if we execute this exhaustive, decades-long search with all the rigor and resources we can muster, and we find nothing? What if we drill the cores, scan the layers, and analyze the atoms, only to find an unbroken record of natural, non-technological history stretching back for hundreds of millions of years, a record interrupted only by our own recent Anthropocene layer? The silence in the rock would be deafening, and it would be just as transformative. To search so thoroughly and find nothing is not a failure. It is a result. It is a discovery in its own right. It would be the first real piece of evidence suggesting that we are, in fact, an anomaly. It would mean that the leap from complex life to high technology is even rarer than we could have imagined. That the confluence of factors that allowed our civilization to arise has perhaps only happened once on this planet. If we find their signature, we gain the humility of being a successor. If we find only silence, we are faced with the terrifying responsibility of being unique. The so what of finding nothing is that it strips away any hope that there are lessons to be learned. From a past failure, there is no precedent. There is no older sibling's diary to read for warnings. There is only a blank book, and the pen is in our hand. This outcome would imbue our existence with a different kind of weight, not the weight of a shared history, but the profound, absolute weight of rarity. It would mean that every decision we make, every conflict we engage in, every environmental choice we face, carries the burden of being the only chance this planet has ever had. The silence of the Silurians would be a command for us to be better, wiser stewards of a gift that may never have been given before and may never be given again, Doc. And so, we arrive at the true purpose of this entire thought experiment. Whether we find the ghost of a lost world or the resounding silence of our own uniqueness, the very act of undertaking the search would transform us. It forces a perspective shift, compelling us to see our civilization not as a permanent fixture of the world, but as a thin, fragile, and astonishingly recent layer of paint on a vast and ancient canvas. It forces us to think on timescales that transcend our own lives and politics. This is the ultimate goal of our work here at the frontiers of cosmic engineering. We use these grand, almost impossible projects as a lens to examine ourselves. The engineering challenge, be it a Dyson sphere, a terraformed Mars, or a search through deep time, is the framework we build to ask the most fundamental questions about our place in the universe. The Earth has a story written in its very bones. Our greatest engineering challenge, our most profound responsibility, and our most incredible privilege is to find a way to read it. The search is not just a means to an end. The search itself is what makes us worthy of whatever answers we find.